Hello, welcome to my presentation. My name is Wei Songwen from Hong Kong Polytechnic University. My supervisor is Dr. Li Xu. Today, our presentation presents a novel method to detect and correct GNSS NLOS using 3D LiDAR sensor before its tightly coupled integration with INS using factor graph optimization. My session is navigation in urban environments. The outline of my presentation includes the background and the overview of our method and the methodology part. Finally, the experimental results and discussion will be presented. GNSS is widely used in many applications such as autonomous driving, unmanned aerial vehicle. However, there are two key issues in urban Kenya. The first one is low availability due to the limited satellite numbers. The second one is low accuracy due to the multipath and NLOS. If a receiver receives the direct signal and the reflected one is in multipath, and only the reflected signal is received, it's called NLOS. This is experimental in urban Kenya of Hong Kong using a U-Blox receiver, and the area can easily reach about 50 meters. Here, this is the ground truth. Here is the solution from the receiver. This is not acceptable for autonomous driving application. According to a recent survey paper, it shows that actually the NLOS is the dominant factor leading to the large errors of GPS in urban Kenya. The shadow matching, very famous method, which proposed to mitigate the effects of non-line sight in urban Kenya. It matches the predicted measured satellites visibility of hypothesis position and with the measured satellite visibility. However, it relies on the satellite visibility classification and the initial guess of the receiver. The range-based method is proposed by the team from Tokyo University. This method using the ray tracing simulation to simulate the signal transmission routes of the NLOS receptions. However, it also relies on the initial guess of the receiver and causes high computation load. In this method, the team proposed using the infrared camera to detect the non-line of sight receptions. For example, in this figure, this is the sky view area, this is the non-sky area, this is the loss, and this is the NLOS receptions. However, it excludes NLOS, which will cause the poor geometry. Similar work is done by this team from Calgary. It's proposed to using the monocular camera to detect NLOS. Similar drawbacks cause poor satellite geometry, leading to increased h-stop. In 2019, I proposed to using 3D LiDAR to detect the non-line of sight caused by dynamic objects, the double-decker bus. The signal is reflected by buildings. However, it relies on the object detection accuracy, and also the field of view of a LiDAR will limit the performance of the NLOS detection. In this work, I go one step further by using 3D LiDAR to detect the buildings, and the NLOS can be detected accordingly. And however, it relies on also the object detection of the buildings, and the field of view of the LiDAR is limited because of the field of view of 3D LiDAR. But how we can relax the two drawbacks? Our idea in this paper is to improve multiple epoch data. First, we replace the sparse point cloud with accumulated map for NLOS detection and even correction. No need for object detection, and enhanced field of view of LiDAR is obtained. Then we use multiple epoch data to integrate the rectified measurement and the INS measurement using factor graph optimization. The overview of the method, it includes two parts. The first part is the 3D LiDAR aided GNSS. We got the IMU, and we can obtain the orientation, the absolute orientation from IMU, the point cloud from the 3D LiDAR, and we can perform the LiDAR odometry to get the map. The map and the satellite measurement as the input, you can do NLOS detection, and the output is the satellite visibility. Then we can do reflecting point detection based on the map and the satellite visibility, and then we will also do NLOS correction and remodeling. The output includes the corrected measurement and the healthy one, and this is the remodeled measurement. Then we do the GNSS and integration. The first factor is the Pseudorange factor, based on the rectified Pseudorange measurements. The second model is the motion model factor, and also the accelerometer factor based on a measurement from IMU. And we also estimate the bias of the accelerometer, and then we do factor growth optimization to fuse all the factors and to get the final state of the receiver. In this page, I introduce how we generate the map. We call it the sliding window map. You can see here, the white point represents the real-time point cloud. The colored one represents the accumulated map, generated map. Here is the skin. Here is the state of the receiver. At each epoch, we get a real-time point cloud. We're using LiDAR odometry based on long algorithm to get the transformation between each two frames. And then we can accumulate the motion to get the map. However, if we want to detect the NLOS, we only need to care about the point cloud surrounding us, about 500 meters. Therefore, we only keep the keyframes, keep the map inside a small sliding window. This is the current frame, here is the historical frame. Therefore, we can find even the tall buildings, the roof of the tall buildings can be detected. Compared with the real-time point cloud, the white one, the point cloud density is significantly enhanced in the map. We can see this is a demo. We can find this is the local map, and the red one is the left side from the satellite to the receiver. Okay, it is significantly enhanced both the density and the field of view of the sensing. In this page, the NLOS detection is presented. Here is the point cloud. The point cloud is the center of the receiver, the satellite. Actually, from the first side, you can find the satellite is blocked by the point cloud. But how we detect it? First, based on the azimuth and the elevation angle, we can draw a line sight from the receiver to the satellite. And then we distribute several searching points, and the distance is 30, which is experimentally determined, and try to find if some point cloud located inside the circle. If no, go to next point. Until what? Until we found there are some point located inside the circle, it means this direction is blocked, and this is the NLOS satellite. Okay, we found the NLOS satellite. Then we do a reflecting point detection based on the NLOS. Okay, first, based on the assumption of previous team mentioned or previous work here, verify that the reflection route should have the same elevation angle with the signal transmission route. Therefore, based on this information, we can draw a direction, and first we detect the loss of a given direction, this one. If it's blocked, potentially this point could potentially be a reflector. Then we will do the reflection detection to find if this direction is blocked or not. If not, we will save the reflecting point to the array. It means this one should potentially be a reflector. And we will search across the azimuth, and after searching across all azimuth angles, we can find an array of the reflecting point of all the potential reflecting point, and finally we choose the reflecting point with the shortest distance from the reflector to the receiver. Based on this assumption, we are usually not always can find the reflector because the map can still only partially reconstruct the environment, even using the proposed LiDAR odometry algorithm. This is a demonstration. Based on assumption, we can get a set of potential reflecting points, but based on the shortest distance assumption, you can find the unique one. Here is a demonstration. Here is the NLOS, and here is the reflector. We only demonstrate one reflector for one satellite here. Here is we found the reflector here. Interestingly, this can also be a potential reflector. Okay, let's NLOS, and here the reflection route. After we do the NLOS detection and the reflector detection, we will do the measurement modeling, the Pseudorange measurement modeling. We do this based on the framework proposed by Dr. Jun. Dr. Jun, the online sensor model validation and estimation framework. The first model is model validation, corresponding to our satellite visibility classification. The second model is calibration. This is corresponding to our NLOS correction. The third model is model repair, corresponding to our Pseudorange measurement deweighting. Okay, the first proposed model is after we detect the reflector, we can estimate the additional transmission delay based on the model proposed by our twins' previous work in here, and we can calculate the transmission delay based on two information. The first one is the distance from the reflector to the receiver and the elevation angle of the satellite, and then we can calculate the transmission delay like gamma. Okay, what can we do if we cannot detect the reflecting point? We can do the deweighting, give a smaller weighting to the NLOS. How we do it? Based on the weighting scheme, this is the original weighting scheme for a typical satellite based on the signal noise ratio and the elevation angle and some parameters, predetermined parameters. For a lost satellite, we're using this weighting scheme. But for a NLOS satellite, we use a scaling factor to deweight the NLOS measurement. This weighting scheme is based on this reference. And then we do the GNSS and integration using factor graph optimization. Here is the factor graph. The state includes the state set from first epoch to current epoch. That's the state set we want to estimate. For a single epoch, the state includes the position of a receiver, velocity, and the bias of the accelerometer and the clock bias, receiver clock bias. Okay, this is the Pseudorange factor, how we formulate it. Here is the Pseudorange measurement, here is the observation function, here is the associated covariance matrix. Here is the observation function can be derived based on the satellite position, receiver position, and the receiver clock bias. Here is the error factor can be derived like this. Here is the observation. This is the expected observation. Here is the covariance matrix. Therefore, this is the error factor for Pseudorange measurement. Different weighting for loss and NLOS is provided here, and the correction is provided here. Therefore, we can derive the factor graph optimization function combining the Pseudorange factor, the motion model factor, and the IMU factor corresponding to here. This is the motion model factor, here is the IMU factor, here is the loss factor, here is the NLOS factor. Okay, after we solve this factor graph optimization function, we can get the final state of the receiver. Experiment validation. We do two experiments in the urban canyon of Hong Kong, the first one and the second one, with the vehicle installing the 3D LiDAR, sensitivity, and IMU, and the blocks receiver. This is for ground truth purpose. Okay, we evaluate the first evaluation is the GNSS standalone positioning based on the receiver, weighted square plus the NLOS exclusion, and weighted square plus the NLOS reweighting, weighted square plus the NLOS reweighting and NLOS correction, and then we evaluate the integration performance. The first one is the EKF, and the second is the factor graph optimization. The last one is the factor graph optimization plus the proposed reweighting and the correction. Okay, we can see in the first urban canyon, the weighted square gets accuracy. The mean error is about 9, and interestingly, the error increased to about 11 meters when we exclude all the satellites. This is due to the increased dot. Therefore, after using the reweighting scheme, we find the error decreased to 9 and to 7 after using both the reweighting and the NLOS correction. Interestingly, the NLOS exclusion will cause the decreased variability due to the limited satellite numbers. And what about the NLOS classification? Okay, here is the different elevation range for the satellite. Here's the percentage of NLOS. Okay, we get the ground truth satellite visibility using 3D building model and ground truth. We can find for this range, we got 92% of accuracy and 35 accuracy for error detection, 21 for this range. Okay, this is a randomly selected epoch. We can find even for the satellite with the elevation angle of 62, we can detect the NLOS, and this is the corrected and this is the ground truth error of the Pseudorange due to the NLOS reception. We estimate error is about 10 and the ground truth is 15. Therefore, the remaining error is still about 5 meters, and with for example, h stop is about 2, and then we get about 10 meters of errors for weighted square. Okay, even the NLOS satellite with an elevation angle ranging from 60 to 90 can be partially detected. It means the high elevation angle satellite NLOS can also be partially detected. For integration, let's see Urban Kenya 2, Urban Kenya 1, we find the EKF solution is about 8 meters, factor graph optimization is 3.6, decreased to 2.8 meters. You can find, compared with the EKF, the factor graph obtains significantly better results. Okay, significantly decreased error. From here, we can find the error decreased dramatically using the proposed method. This is due to the proposed error detection and correction method. Due to the correction contribution from the NLOS correction and the remodeling. Okay, since we find the factor graph can outperform the EKF dramatically, we open source our core using factor graph optimization to process the GPS measurement, and we also open source our data set. Okay, the open source core is still under submission to the GPS solution. The data set is collected in Urban Kenya of Hong Kong. Okay, in Deep Urban Kenya 2 experiment, we can find the similar improvement is obtained. Interestingly, the NLOS exclusion is also leading to a worse result from 23 to 25. After we applying both the correction and the remodeling, the positioning error decreased from 23 to 17 meters. Okay, here is a demonstration for NLOS detection, and this is the experiment environmental for experiment for Kenya 2. For the GNSS integration in Urban Kenya 2, you can find the error decreased from 20 meters to 18 meters to 30 meters finally. This shows the effectiveness of the proposed method. You can find here the error decrease dramatically. This is due to the contribution from the proposed NLOS correction and remodeling. Okay, also we can find the blue one represents the proposed method. The ground truth, the proposed method is significantly better. While the remaining errors still reach about 10 meters. Okay, we dig into the data. We randomly select an epoch we find. The multipath error can reach about 34 meters. It's pretty large. Okay, therefore, we believe in the future work, we also explore to study how a proposed method can help to mitigate the effects of multipath. In this data, we use the double difference technique based on our team's previous work to get the ground truth error of the multipath. Okay, here is a demonstration. The satellite is actually based on our method. We found it's a lost satellite. Actually, it can also be reflected, leading to a multipath effect. Conclusions and future work. In this paper, we relax certain drawbacks of the previous method using 3D LiDAR aided GNSS positioning method. In the first one is that our method do not rely on the object detection, and the field of view of 3D LiDAR is significantly enhanced. We're using multiple epoch data to integrate with INS using factor graph optimization, and improved accuracy is obtained. The proposed method effectively rectifies the Pseudorange measurements. Significantly improved accuracy is obtained in the integration. In the future, we are going to study the potential of the proposed method in GNSS real-time kinematic positioning. Moreover, we will also integrate the LiDAR odometry with the proposed method. Thank you.